Welcome to the lectures on modern digital communication techniques. So, we have covered a very important aspect in the previous lecture, and summarily, if you would like to see what we have done so far in a nice way, we could briefly state that we have started with the transmitter. We have seen one channel at least where there is additive noise, and we said that this is not completely theoretical, it has practical usage. So, it is not simply a fancy that is what we are doing here. And then not only that, we have started looking into the receiver, and at least we have covered a stage where we have reached the first part of the receiver, which is the demodulator. So, in the demodulator we have seen two different kinds, the correlator and the matched filter, and what we see, the matched filter uses an H, the impulse response, which is the flipped version of the correlator function, and rather it is Hk, that is the kth filter is that of the kth correlator or the basis function. And we have seen one of the important characteristics of matched filter is that by choosing an impulse response which is matched to the signal, in our case matched to the basis function, what you get is the output of the matched filter at this point has maximum signal to noise ratio. So, this is a very important stage where we are. So, once we discuss the detector, then at least we have travelled one path from the source encoding, transmission of signal through modulation techniques, passing through an AWGN channel, and the receiver procedure, through which one should be able to realize a basic transceiver system. What we have not covered is non-ideal situations where there is channel estimation required, channel equalization required, and carrier synchronization and clock synchronization required, which we will do after we complete the receiver discussion, as well as study the performance evaluation in terms of error probability once we complete the AWGN receiver. So, proceeding further, this briefly summarizes what we have done earlier. So, it is the same picture where received signal sent to a parallel bank of filters. Each filter uses the basis function in the flipped fashion as the impulse response. So, when it goes through the filter, there is convolution of the flipped function is as good as correlation. So, the output at the sampling time t, which is the symbol period, we get the component of R on this basis function. So, we get all the components that are desired. So, if this is the signal, the matched filter would be the flipped version, that is what we have here. And when we discuss the properties of matched filter, we looked at the filtering operation, which is convolution, and then received signal is broken into two parts, the desired signal and the noise component, and then we computed the signal to noise ratio of the signal component and the noise component, where we defined signal to noise ratio as the power of the signal to power of the noise. We computed the noise power, which turned out to be N0 by 2 multiplied by the energy of the impulse response. So, as long as the energy is kept constant, the denominator would be kept constant, and our problem was to maximize signal to noise ratio at the output. So, that to maximize the signal to noise ratio at the output by choosing h of t, because signal is not in our control, only h, that is impulse response, is under control. And then we see that denominator, if it is to be held constant, then we are only left with the numerator. So, when we look at the numerator, that is this portion, we use the Cauchy-Schwarz inequality. Using the Cauchy-Schwarz inequality, we find that the maximum value of this is attained when one of the functions is a scalar multiple of the other function. So, that means h of t should be equal to some constant times s t of tau. So, that means to maximize, you need to have the filter which is matched to the signal. We already started with the premise that let h be matched to the signal, and now we are saying that if you want to maximize the output of the matched filter, you must choose impulse response in this fashion. So, what we have here is, if you choose it in a matched fashion, your SNR is maximized, and the maximum value of SNR is 2 E by N naught, where E is the energy of the signal. This is a very, very important result in the study of digital communications, which we should remember. So, moving down further, let us look at the frequency interpretation of the matched filter. So, what we have is, since h of t is matched to the signal, h of f, which is obtained by Fourier transform of h of t. So, we have the Fourier transform of s t minus tau here, and then by change of variables, you could do a sequence of change of variables. You would find, you could write this at s of tau e to the power of j 2 pi f tau, right. And recall our discussion in the beginning, where we stated some of the Fourier transform relationships. So, this is equivalent to the Fourier transform conjugate of S of f. So, S of f is the Fourier transform of S tau. So, S conjugate of S f would be something like this. So, and there is a phase term, of course, there is a phase term e to the power of j 2 pi f t, you would easily get it through translation of variables, change of variables. So, this phase term is because of the sampling delay, because we sample the signal at the end of a certain sampling duration, which is t. So, you would remember that there was a sampling gate, which we said at t equals to capital T, you sample the signal, and absolute value of h is the same as absolute value of f. So, there is no problem to it. So, this is the frequency domain interpretation of the matched filter, and you could calculate the signal to noise ratio even in the frequency domain, the results would turn out to be the same. So, these are some of the important things we should remember. With this, let us move forward and let us take an example on matched filter. So, to take the particular example, what we do is we consider two functions f1 and f2. So, this is f1 and this is f2. So, f1 is having a value which is root over 2 upon t up to t by 2, and it is 0 for the period t by 2 to t. f2 is 0 in the interval 0 to t by 2, and it is non-zero or having the same value as f1 in the period t by 2 to t. So, looking at these two, one of the important conclusions that you can directly make is that these are orthogonal to each other, clearly, because if I multiply f1 with f2 and integrate for the period 0 to capital T, what will you get? 0, there is a non-zero value, but there is a 0 value. So, up to this point, this has non-zero value, however, this has 0 value. So, therefore, the product is 0, and from t by 2 to t, this has non-zero value, but this has 0. Combining, you have a 0 value in the entire range. So, that clearly means it is orthogonal, and otherwise it is visibly also available. So, this would also mean that one could choose this as the basis functions as well. So, which is a different realization of a basis function. You have seen basis functions in the I and Q domain, that means one that modulates the cosine carrier, one that modulates the sine carrier, but now you are seeing that you could find basis functions in the time domain also. So, it is not new. If you are very careful, you will note that we discussed n dimensional signaling. When we discussed n dimensional signaling, we said that a certain duration of time could be divided into time slots, and you could send a signal in one of the time slots, do not send anything there. You could send signals in one of the time slots and not send anything there, and like that you could have it in this manner, right. So, if you have it in this manner, in that case these signals are orthogonal to each other and you have n signals. So, we have two signals which are orthogonal to each other and created in the time domain. You could in this fashion create a longer duration of time and divide it in, and you could also create n orthogonal signals. So, this is in the baseband form. So, F1 and F2 are used for transmission over AWGN. That means, to send signals over AWGN, you could either choose F1 or F2 to indicate the presence of a 0 or presence of 1. And of course, what we have is the power spectral density is n naught by 2, and if the question is what are the basis functions. So, clearly as discussed just now, these are the basis functions already, and represented mathematically, it is F1 of t is equal to this amplitude root over 2 by capital T, it is a constant in the interval 0 to capital T by 2. So, that is it is a constant value in the interval 0 to T by 2 and 0 otherwise. And F2 is the basis function, which is this constant amplitude root over 2 by T in the interval T by 2 to T and 0 otherwise, right. So, this is mathematically represented, and then we would ask what is the impulse response of the matched filter. So, the impulse response of the matched filter would be very interesting here. So, we have to get back to the matched filter structure. So, if there is a receiver, we should have, there are two basis functions. So, we should have two filters, and this clarifies some of our doubt that this one should be F1 of t minus t, and this should have the impulse response F2 of t minus t. So, this is H1 of t. So, that means we are using impulse response as the basis function and flipped version, right. So, that is exactly what we have, that is H1 of t is equal to F1 of t minus t. So, if you put t minus t over here, so you have to put capital T minus t over here, and that you will be getting as root over 2 by t for the interval t by 2 to t. So, if you are going to flip it around t, so it is going to go there, right. So, you can put the values and you will clearly get this thing. Yeah. For same for F2 t, the second impulse response would be F2 t minus t. So, F2 t minus t would take this value for the interval t minus t lying in this interval, right, small t minus capital T lying in capital T minus small t lying in this interval. So, if you put that inside this, you are going to get that for the interval small t in the interval 0 to t by 2, it is non-zero. That means, you are going to get H2 t as, sorry, we could draw it here. So, you would get H1 of t as this thing, and H2 t you are going to get it as this, and here the value is root over 2 by 2, here it is root over t by 2, here it is 0. So, this part it is 0, look at this, the matched filter is this one, and for this one the matched filter is this one, right, it is 0 over there. All right. So, you could construct matched filter in this fashion, and then the output waveform of the matched filter, if you have to see. So, there is noise, of course. So, one could see the noisy response, but what we are interested now is the noise free response, that means only the response of the signal, that is what we want to see over here. So, it is the outcome of the convolution from 0 to t s of tau h t minus tau. So, because this is convolution. So, if S1 is sent, Y1 of S will be equal to, that means output of the first match filter will be F1 of t, right, that means this is the signal that is sent convolved with this one, and the output of the second matched filter would be the signal that is sent if first signal is sent convolved with the second matched filter, right. So, what you are going to get if you solve this, then you would, if you would work it out, the first matched filter will give you an output like this, and the second matched filter will give you an output like this, which when sampled at t equals to capital T, the first match filter is going to give a maximum value, which is a square root of t by 2 or square root of a squared t by 2, whereas the output of the second match filter will be 0. And that again tells you that the second matched filter is orthogonal to the signal, because at small t equals to capital T, that means at this point the signal value would be 0, whereas this one, the first match filter, is going to give the peak value. So, remember we found that is going to give the highest signal to noise ratio. So, noise power is constant, but signal power is maximum only when the integration period is capital T. So, these are the outputs that you are going to get from the matched filter. And of course, in the previous page we had this in the y axis, which is the energy. So, you could calculate that, and this clearly we have shown in the graph in the previous page. We have clearly shown this in the figure here, right. So, that should help. y1s at t equals to capital T is equal to this value, and y2s at t equals to capital T is 0. That is what you have over here, it is having a 0 value, right. So, now in the vector form, this is important. So, the vector received from the matched filter, remember we are trying to draw r of t, right. We are having r of t being passed through one matched filter to another filter, sampled at t equals to capital T. So, whatever value you have here is r on the first dimension and r on the second dimension, and together you get the vector r, which is r1 r2, right. So, this is the vector dimension that you get. So, this is the outcome of the matched filter. So, that is what we have over here. The vector received from the matched filter output is r1 and r2. r1 is the output of the first matched filter, which will be, this is the signal part, that is what we said, right, and there will be the noise part also. We did not do the noise calculation in our exercise here, we did only the noise free part. And what will be the noise part? The noise part will be n tau h t minus tau d tau, and that would be the component of noise on that basis dimension, and that we write it as n1. And the outcome of the second one, again back here, it will be noise with h2, and we will write it as n2. So, that means the outcome of the first matched filter will be this signal plus there will be noise, and in the second matched filter the outcome will be 0 from the signal component, 0 from the signal component plus noise. So, it's should not be, although I do not have it here, but we should be remembering these things, that R t is equal to, so S m t plus n t. So, whenever we are convolving r tau h of t minus tau d tau, whenever we are doing this, in that case we are basically doing integral S m tau plus n tau, I will write in short convolution with h, right. So, that means the first part of the integral is already shown over here, that means S convolved with h t. So, you also have noise convolved with n t, and in the second match filter this convolution integral results in 0, while the noise component we mark it as n2. So, that is what we have. So, we have n2. So, now we could write that n I is whatever we have over here, n1 or n2 is y I n, I taking the value of 1 or 2 at time instant t. So, this is basically the component of noise on that basis dimension, right. This is what we receive. Now, if we would have sent the second signal, that means now we are talking about sending S1. if we send S2, that is the second function, second waveform, what shall we have received? We would have received not this, but the first, instead of this one, we would have received N1 from the first matched filter, because we have sent second symbol which is orthogonal to the first basis dimension, and we would have received signal power plus noise in the second thing. So, this would be my vector R if I would have sent symbol 2, right. So, this is just for clarification. So, now since we have got the receiver, since we have got the received vector, we are now at a stage to discuss the receiver. That means, we said already we have the diagram here. So, we have completed the demodulation, the correlation matched filter. We have seen what kind of output the matched filter gives. So, it gives a vector R. We said it gives a vector R. The detector uses these components to decide which waveform it has produced. It produced these waveforms. So, just to summarize, look at this. S of t can be represented as sum of Sk Fkt, correct, where Sk are the components of St of S on Fk. So, Sk is equal to integral 0 to t St Fkt dt, right. Achha. Similarly, Rt can be represented as sum of Rk Fkt dt, where Rk are the components of Rt on Fkt dt. So, this is what we know, and this is what we have achieved over here. So, Rk means the component on the kth dimension, and k is equal to 1, 2 up to capital N. So, there are, so R of t is composed of these components along with those basis dimensions. So, what the matched filter does is decomposes R as the components along the dimensions. So, what it produces is the vector R made up of component in the first dimension, on the second dimension, up to n components, right. Now, since we have produced these components, and just a side note, the way it produces the component maximizes the signal to the noise power, right. The next part is now ready with us. So, since we have got these components here, it goes to the detector. The job of the detector will be using these components to reconstruct the symbol. Please note it, it has these components. So, from components you can find Rt, right, and Rt is made up of SMT and noise. So, Rk is made up of, this we have seen already, is made up of noise. So, that means, if I have Rk, I also have Smk. If I have Smk, that means the kth component of the mth signal for k equals to 1, 2 up to n, that means for all k and for a particular m. So, if I have all these components, then I can construct St, right. So, what I mean to say is, if I have these components, I know which waveform was sent, right. So, I could modify this expression and put a sub m and put a sub m. So, if I have all the components, I know which particular mth waveform has been sent. However, the problem at the receiver is my information is noisy. So, from my noisy information, I have to find out which particular waveform was sent. So, this is the problem that is available at hand. That is what we are exploring. So, that is the job of the detector. So, at the detector, here we discuss the optimum decision rule based on the observation R, right. So, this should be very clear now. So, we have generated R. So, if you look at what we have generated in this page, we have simply got components of R on the basis dimension. This is what we have got, right. And now, since we have got all these components, we want to find out which SM, because these components contain the signal, but it is noisy. So, we want to find this out. So, there is a decision making process, because we have several SM of t, where m is equal to 1, 2 up to capital M. You have this problem. So, given this set, you have to choose what is the value of m that was sent. So, I would probably do it once again in a little bit better way. We have S1 1, we have S1 2 up to S1 n. This is the vector S1, that is the signal S1. So, I can construct S1 of t by a linear weighted combination of these components along with its basis function. I have S2 vector as S2 first component, S2 second component up to S2 nth component, right. Like that, I can have Sm as Sm first component, Sm second component up to Sm nth component, and I can go to Sm different waveforms. K bits are required, log of m base 2. Look at this, mth signals, nth component. So, now what we have stated here is we have these components for a signal, but these are noisy. The moment these are noisy, what is going to happen? One signal might look more close to another, right. The moment these are noisy, I actually have sent this, but some of the components might be similar to another waveform, and then I have to choose which of these waveforms was transmitted based on this noisy. So, there is a decision, there is a choice that has to be made, you have to choose amongst these, right. Whereas, in the first part that we did here in the demodulation, there is no choice, there is simply a straightforward computation. I have RT, I simply project it, whatever I get, I do not make a decision. So, now we have changed the problem and we have a decision making issue coming into. You have to choose between one of these options, right. You can't choose something which is somewhere between S1 and S2. It has to be any one of these choices. So, for example, if I have, let us say, QPSK, right. So, there could be a waveform like this, there could be a waveform like this, and there could be 4 other waveforms. The detector has to choose any one of these waveforms and it has to identify probably this was sent, it can't do anything else. It cannot say, oh well, something of a waveform which is none of these 4 has been sent. In terms of baseband constellation, it has to select one of these options. It can't say that, oh, something in between has come, which is actually done by the first part. If you look at the first part actually projects the signal on the I axis and on the Q axis, right, on the basis dimension. So, whatever, suppose I have sent this, and noise gets added. So, noise will get added in the I dimension as well as in the Q dimension. So, suppose the received signal is here. So, what the matched filter does, it projects this signal here as well as it projects this here, and it tells that the vector is composed of the value R1 and R2. Now, using this R1 and R2, the receiver has to decode, right. So, the other situation can be this was sent, but noise got added and the received signal has in the vertical direction shifted here and in the horizontal direction it is shifted here. So, suppose the received signal has come here. So, it will produce R1 over here and it is going to produce R2 over there. So, this has a vector R1 R2. The job of the detector would be, having given this value, to find out or to tell which of these 4 was sent. In the previous example, if this was produced, the job of the detector would be to choose any one of these 4 given that this is received or is the output of the matched filter. So, with this distinction, we would like to stop this particular lecture here, and we will discuss the optimum detector in the optimum detector, that is over here, in the next lecture. Thank you.